Like I was saying, today we're going to keep on learning about simple harmonic motion, getting more practice doing the problem solving associated with converting between period and frequency, and also plotting harmonic motion on a graph and identifying the key features of harmonic motion from those graphs. So at the end of class, we talked about what it would look like if you were to take an object in harmonic motion, like the spring bobbing up and down, and you were to plot the vertical, the displacement of the spring from its equilibrium position. If you were to plot that against time, the graph that you would get would look something like this graph right here, where on the vertical axis, you're plotting the distance, or really it's the displacement that the object has been moved from its equilibrium position. If that spring is just hanging there before you pull it, it hasn't been moved at all. So its displacement is 0. And then if I take that object and I pull it down or I pull it up, it will have some sort of displacement from equilibrium. And once you release it, because of the spring wanting to bring that object back to its resting position, it's going to bob up and down and be in a form of harmonic motion. And if you graph how that object moves up and down as time moves forward, this is the graph that you get. And all of those features of the harmonic motion can be shown on the graph. If we think about the amplitude as the maximum distance that the object is moved from equilibrium, if 0 is where we're at equilibrium, then the amplitude is just how far we've moved, either below it or above it. And you'll notice that no matter how you look at that, whether it's how far maximum distance above equilibrium or below equilibrium, either way, that gives us the amplitude of 4 centimeters. A cycle is basically just one repeat of the motion, right? It was, if you got this object moving up and down in simple harmonic motion, it's a repeating form of motion. And you can look at basically any point in this motion and find where the motion repeats. If you look at, like, say, the very bottom part of the motion, when the object is at the very bottom, it starts to move up. And a full cycle would mean returning to the same position with the same speed and direction. So if I'm starting at the very bottom, a full cycle from here would mean moving all the way up to the top and then coming all the way back down and returning to the bottom again. Same speed, same direction, same position. This point and that point would show me a full cycle. In other words, from there to there, going through the motion is one complete cycle. And the period is just the time that it takes to go through a complete cycle. So if this point and that point show me a full cycle on the graph, the period is the amount of time that separates those points. And if I look at this point right here, and I look at this point right there, the time that separates them, I'm starting at 0.25 seconds, and I'm ending at 1.25 seconds. So what separates these points is 1 second. It takes 1 second for my object to go through a complete cycle of motion. So that's the period. The period is 1 second. And it's the time for one cycle. And so there's lots of different places on the graph that you could look at to find the period. I could start at this top here. And then a full cycle would mean returning to that same position with the same speed and direction, which would mean this peak here. Going from peak to peak will give you a full cycle. Going from trough to trough will give you a full cycle. And what separates a peak and a peak, or a trough and a trough, is, if we're plotting the wave against time, what separates those 2 points is the period. Time for that complete cycle. So if I start the cycle at 0.75 seconds and I end it at 1.75 seconds, the period is still 1 second. And then, so that's talking about amplitude, cycles, periods, and then the frequency, that's just the number of cycles that are completed in 1 second. So you would basically look at, where does the graph start? Where do I have 1 second on the graph end? And then you would count up how many complete cycles does my graph go through in 1 second? And that number of complete cycles is your frequency. So we go through, looks like we start at equilibrium. And at 1 second later, we've returned to equilibrium, and we're also moving downward. So in other words, 1 full cycle is completed in 1 second. So if you do 1 cycle per second, then your frequency is 1 hertz, because that's the definition, 1 cycle per second. You could have also, sometimes for me, I honestly think it's easier to just, if I find the period on the graph, t is the period, which is 1 second. I find it a lot easier to just say frequency is 1 over the period. And that's something you can always do. And if I do 1 divided by 1 second, 1 divided by the period, then my frequency is going to come out with 1 hertz. So yeah, 2 different ways. Once you know the period from the graph, you can use the formula to find the frequency, or you could count how many full cycles there are in 1 second. Either way, that's how you could get the frequency. So that is how we can do harmonic motion on a graph. And what I wanted us to do today is get some practice with both the problem solving in terms of like converting between period and frequency, identifying harmonic motion, as well as doing these graphing problems. And the way that we're going to do that is with a worksheet that I posted on Google Classroom. So if you go, and I'm going to change my screen real quick and pull up Google Classroom. If you go onto Google Classroom under classwork, under the simple harmonic motion topic, there is an assignment called Simple Harmonic Motion Worksheet. And if you go in here, the front page of the worksheet just includes like all of the important information that we've talked about in terms of our definitions, our calculations, some examples, also talks about the graphing. And then on the second page, there's some questions for you guys to answer. And so identifying, is it harmonic or is it linear motion? Definitions, converting between period to frequency or frequency to period, and then some graphing problems. And we've already spent a good amount of time talking about our definitions, doing these period and frequency calculations, but we haven't done any of these graphing problems yet. So what I wanted us to do is work this first graphing problem together as a way for us to make sure that we see how to put all those pieces together, and then we'll have the rest of class time to finish up the other parts of this worksheet. So what I would like you guys to do is to go on to Google Classroom, get that worksheet, and we're gonna need to turn that completed worksheet in, and there's a couple different ways that you could do that. If you have your iPad and you have a stylus or a way that you could like draw or write on the document using your iPad, you could do that. You could always just read the problems on the screen and then work the problems on paper. And as long as you can show your work, then that'll work fine. You could print the document if you have a printer and work the problems that way. And really any other method that's going to allow you to show your work on the graphing problems and submit those problems as well as your answers to the other ones is going to be fine by me. The main thing is that I want to be able to see the work that you're showing to like answer the graphing problems. And also I just want to see that you're answering the other questions as well. And so I'm going to walk us through that first graphing problem so that we are all on the same page in terms of how those go. And then we'll go from there. So that's the plan. Take a minute or so to get that first problem pulled up in a way that you can work on it, either by working on it on the screen on your iPad, just copying the problem over, printing, or however you want to do it. But that's going to be what the plan is. Ideally, if we were in the classroom, I would just give you the worksheet and then you could do it that way, but kind of gotta make do with what we got. So any of those will be acceptable, and really any way that if you can show me the work, then that'll be fine. And so the first graph looks like this. One second, so get that pulled up, Sadakova's calling me, and then we'll go from there. Okay, false alarm. All right. So here's our graph, here is our questions. And let's just go through them in order. We're shown this graph, and the first thing they want us to do is mark one cycle of the harmonic motion. And so if they say mark one cycle, let's see. When they say mark one cycle, that basically just means, at least the way that I'm going to show it, is I'm just going to trace a full cycle out on the graph. So one way that you can do a full cycle is going from a peak of one wave to the peak of the next one. So that's one cycle. Going from the peak of one wave to the peak of the next one. So that's all you really got to do when they say mark one cycle of the harmonic motion. And you know, there's a lot of different, there's essentially like an infinite number of ways that you could answer that first part. Because you could go from the peak of this one to the peak of that one. You could go from the peak of here to there. You could go from the trough of this one to the trough of that one. But you could also pick any interior point and then go to its next point along the cycle. As long as you return to the same position, moving in the same speed and direction, you could define a cycle to start wherever you want. You know, if I wanted to start a cycle right here, then all I need to do, and I want to go this way, then all I need to do is return to that same position with the same speed and direction. So it wouldn't be here, because that's returning to the same position but not moving in the same direction, because at this point I'd be moving down. A full cycle would mean returning to the same position, same speed, same direction, so also moving up. And if I were to trace that out on the graph, that would also be a full cycle, going from there to there. And so as you can see, you could pick whatever starting point you want, as long as you end up completing the cycle. There's a lot of different ways that you could do that. So I just showed you two different ways, but that's what they want you to do when they say mark one cycle. Number two, they say starting at 0 seconds, when does the first cycle end? And when they say, when does the cycle end? When, that language is asking you about time. In other words, like if the first cycle is starting at t equals 0, our first, oops, let me do it like this. Our first cycle is starting at t equals 0. When does that first cycle end? And so at t equals 0, we're starting at a peak. That means that we're going to end up, the first cycle is going to end at that next peak. So when does the cycle end? Well, we started at 0 seconds. We ended up at 1 second. So the cycle ended at t equals 1 second. And that also happens to be the period, right? That was the time that it took us to complete one cycle. And if I would have looked from this point to that point, it would also be 1 second. I just picked an awkward kind of place to start looking at the time. But if I looked at from this point to that point, it's also going to be separated by 1 second. Starting at 2, ending at 3, 1 second of time passed going from there to there. So that's number 2. Number 3, they're asking us for the number of complete cycles. So starting at the very beginning of the problem, how many complete cycles can you get? So going from the peak, starting at a peak, going to the next peak, that's one cycle. Let's see, one cycle. Going from this peak to the next one, that's two cycles. And then going from the second, I guess going from the third peak to the fourth peak, that's our third cycle. So there are 3 complete cycles in the graph. Notice it's asking for the number of complete cycles. So you would only answer a whole number. And like if the graph were to continue on a little bit, you would only answer the number, it's just whole number of cycles. And if you didn't quite get to the third one, like say the graph cut off right there, and we didn't complete the third cycle, then the number of complete cycles would have just been 2. So that's the number of complete cycles just from the starting point counting cycles till you get to the end. Once we've got those things answered, that's the questions that are not as directly familiar with what we've already been talking about. Period, frequency, and amplitude. Hopefully those are a little bit easier to identify. When we talk about period, that's just the time for one cycle. So there's a lot of different, just like there's a lot of different ways to trace a full cycle, there's a lot of different ways you could identify what is one period. But it's just the time to complete a cycle. So like if that was one cycle, then one period is just the time to complete that cycle. That's a period. That's a period. That's a period. Also, that's a period. It's the time to complete one cycle. And as you can see, whether you start here, or there, or there, one complete cycle, as long as you count it correctly, is completed in 1 second. So the period, time for one cycle, is 1 second. The time that separates any 2 peaks, the time that separates any 2 troughs, the time that separates any 2 points that give me a cycle. 1 sec. Hello? Okay, sorry about that. All right, so that was a period. And if anyone has questions now or about any of those things, definitely let me know. But yeah, once you find the period, like I was saying a second ago, there's 2 ways you can find the frequency. The way it's defined is the number of complete cycles in 1 second. So if you can count how many cycles there are in 1 second, that's one way you could answer it. And on this graph, it's really easy because we complete 1 cycle in 1 second, which means the frequency is 1 hertz. You could also use the formula. And if you do frequency is 1 divided by the period, you do frequency is 1 divided by the period, then it's 1 over 1 second, and that would be 1 hertz. Hertz is just the unit for frequency, and that means cycles per second, or it's really 1 over. It's units of cycles per second, but cycles aren't a real unit, so really we just call them hertz. The 1 over seconds that we get from this unit right here are what we call hertz. So that's our frequency. And last but not least, they want us to find the amplitude. And the amplitude, that's just the maximum distance from equilibrium. If you start at 0 and go up, how far do you go up? Or if you start at 0 and go down, how far do you go down? And so it looks like if we start at 0 and go up, it's 6 centimeters. If we start at 0 and go down, it's also 6 centimeters. So the amplitude going from 0 up to the peaks or from 0 down to the troughs, that distance from the equilibrium to our maximum or our minimum points is that distance is the amplitude, and that is 6 centimeters. Great question, Nicole. So if it's not the same number up and down, you can do kind of like an averaging thing. And that's actually shown on the previous. So if it's okay, real quick, I'll go back to the previous slide. If you have a high point and a low point that are not symmetric with 0, then you can basically just do 1/2 of the high value minus the low value. So just like as an example of that, if I've got a wave, but instead of starting at 0, it starts at 10. And does something like that, then it's not, then my equilibrium is actually in the midpoint. And so if 0 is the bottom, and I didn't know, because you know how to do averaging, if it's basically the midpoint. So that's kind of like what this formula is doing. And if my high value is 10 and my low value is 0, then I'd be doing 1/2. Oh, and then I'm getting caught by the bottom here, 1 sec. To find that amplitude. To find that amplitude, I'd be doing 1/2 of the high value, which is 10, minus the low value, which is 0, and that would give me 1/2 times 10, which is 5. So that's, really, you're using that formula. And it's essentially just finding the midpoint between the highest value and the lowest one. But yeah, I think that's an excellent question. So yeah, if you need to handle it like that, that's how you would do it. Okay, and so that's the completed example for number 1. And I think all of the other ones, I mean, like, the questions have different graphs, but the way that you approach the problems is very similar. So as long as we're following how we're putting these pieces together, we should be in a pretty good spot to be able to finish up those questions on our own. And that's what you guys have the rest of class time to do. So my hope is that we have the rest of class to use that time to practice, get our questions answered, and learn from any mistakes if we end up making them. So you guys have the rest of class time to work on that worksheet and to get it completed by, basically, it's set to be due by the end of the class period, or sorry, it's set to be due for tonight at midnight. And so yeah, you guys can work in groups if you want to. If you have people that you'd like to work in a group with, just send me names and I can put you guys in a group. But yeah, the plan is to use the rest of class time to work on those things, to ask me questions, and if you get stuck, or if you want me to check any of your answers, you could let me know about that too, and I'd be happy to give you feedback about if you're right, if you might need any adjustments. Yeah, the other things I wanted to quickly mention is you've got the focus notes over simple harmonic motion that were due last week. Please do finish those if you haven't got them done already, because that's a daily work grade that's going to be going into the grade book this week. We also started homework 29 last week, and that's still up right now, and that should be easier to do now that we went through those warm-up problems. So also, you could be working on that. But But yeah, that's basically the plan for the remainder of class time, is to be working on the harmonic motion worksheet, and to let me know if you guys have any questions. So yeah.